Welcome to lesson 4 of unit 6. So you're getting really close to the end. We're almost done this unit, and then there's only one more. We're looking at sketching graphs of rational functions in this lesson. So kind of working our way back to those rational functions that we looked at earlier in the unit. So sketching rational functions, there's some key things that we need to watch out for. We've got watching out for holes and vertical asymptotes, and that's going to be a really important part. And we do that by using our non-permissible values, okay, determining the equation of horizontal and oblique asymptotes, and establishing the behavior of graph near the asymptotes. And then, of course, any intercepts, if there are any. So for our first example, we can first look at just factoring out our numerators, see if there's any way that we're going to get any canceling going on to try and figure out if we've got holes or asymptotes going in this function. So if I factor this out, it is -1 and -4. And because I've got that -1 and I'm noticing that's very similar to my denominator, what I'm going to do is I'm going to take out that negative in the denominator and turn that into x minus 1. And what that allows me to do is then cancel out these two terms to simplify the function that I'm actually going to be graphing. So instead of graphing this big rational function, I'm only working with negative x minus 4, or if you want to rewrite it as negative x plus 4, whichever one makes more sense to you. Okay, but this is our simplified version. And I still need to be true to my non-permissible value. So even though it's disappeared, my non-permissible value still needs to be acknowledged. So that is when x minus 1 equals 0. So x equals, sorry, not 0. Getting all excited about nothing. 1. So that is going to be my non-permissible value, or x cannot be 1. But what I need to note here is because it's canceled, it's going to be a hole, not an asymptote. With all of that information, and the fact that I have no asymptotes, only a hole, and otherwise it looks like a linear equation now, this should be relatively easy to graph. My y-intercept, going back way to like grade 10, knowing y equals mx plus b, my y-intercept is going to be positive 4. Again, labeling graph with my scale. And then my slope should be -1. So in terms of rise over run, it's going to be 1 and 1 going down towards the right. So go down 1 over 1, down 1 over 1, and that gives me my relative line, and I should have my x-intercept then over here, but remembering that x cannot actually equal 1, so where I've put this point, I would expect a hole. And that would be my graph, and you would want it to be straight. So things you might do with a pencil is you might actually just draw the whole line and then erase and put your hole in after. The only struggle that I have on these surfaces is that I can't actually erase part of the line. I'd have to erase the whole line, and it becomes an issue. So my line's a little wonky. You would want yours to definitely be much more straight, and then erase and put the hole in after would be my suggestion for drawing. Once I've done this, I've been asked to state my domain and range, so don't forget to do that. The domain of this function is from -infinity to 1. 1 doesn't exist, united with 1 going to positive infinity. Again, if you want to use interval or set notation instead, you would say that x is an element of the reals, but that x cannot be 1. My range, in terms of interval notation, would be from negative infinity pointing downwards up to positive 3, united with 3 all the way to positive infinity. And again, I'll do set notation for this one just kind of as a refresher. It's not x, it's y, but y cannot be positive 3. And then we're done that question. So these ones are my favorite, the ones where we get canceling denominators, because it simplifies the question, that the shape that we're ending up graphing, and it also simplifies just how efficient we can be. Example 2 is not going to be as nice because we got to watch out. We've got matching degrees. I can't factor it, unfortunately, in terms of canceling, but I am still going to factor out my function so that I can see what my non-permissible values are a little bit easier. So this is a difference of squares in the denominator. So I'm going to end up with plus 5 and minus 5. So my non-permissible values are going to be when x cannot be positive or negative 5. Because I've got no canceling, these are going to be asymptotes. If you recall from our previous lesson, when we have matching degrees, that means that we need to check our horizontal asymptote. And so when we're doing that, we're going to do synthetic division, or you might just be able to remember that it's going to match our kind of like ratio of coefficients with that degree. So in this particular case, it would be negative 2. But just in case you don't remember, we were going to do synthetic division. Synthetic division here would be a little bit awkward, but you can, yeah, I actually wouldn't recommend it just because it is a square term. So being able to remember that ratio piece. So my horizontal asymptote is going to be at y equals negative 2. So with all of this, I can sketch in my asymptotes already. Now, we're told that we need to find any intercepts, so we need to bear that in mind as well. So we might have some x-intercepts when y equals 0. That would be also x equals 0. And again, you can plug and chug to figure that out, what that would look like. Would be 0 equals negative 2x squared divided by x squared minus 25. Multiply this out of the denominator though, and that disappears. The negative goes, so does the 2. Square root of 0 is 0. So that's where that value came from. Okay, and then that also solves for my y-intercept, so that's kind of nice. From there, we can test some values to see kind of like what we would expect to be happening in this graph. And what we're going to see is we can make a table of values and just plug and chug if that makes sense to you. Negative x and y, negative 7, negative 6, negative 4, negative 3, negative 2. And that should give us a good picture of like what to expect on our graph. So if you plug these values in, I would say use a calculator just for expedience sake, and you'll get some good values. Okay, and once you have these values from your calculator, you can then proceed to graph them. So I know that I'm going to need to extend my scale along my y-axis a little bit. And again, make sure you label your y and x-axes for graphing. So negative 7 and about negative 4 is here. Negative 6 and about negative 6.5 would be here-ish. So I'm expecting this shape to kind of look like this. Then between my two asymptotes, I'm going to get some symmetry going on with these values. So 2 is like not even at negative 2 is not even at 0.5. Negative 3 is at just over 1. And negative 4 is at positive 3.5. So we get that kind of parabolic shape going on again in here. And I would expect a similar kind of piece. And again, making sure that it goes actually all the way down to 0 there. And finally, I would expect a similar kind of effect over here, because we do expect symmetry with our graphs. That's what I would expect to see. Something along those lines, a little bit smoother. There we go. Okay, so that's kind of how we would sketch one that has a matching degree. Now, if we have that higher degree in the numerator, that's where we're going to get our oblique asymptotes instead of horizontal asymptotes. But before I start trying to negotiate that, I'm going to double check to see if I can factor it out in a way that lets me cancel out that denominator. So in terms of my factors, it ends up being like this. And you can factor out this complexly, do some work on the side, whichever strategy you want. But I see that I do not, unfortunately, get to cancel anything else. So it's too bad, disappointing. But I am going to work with this in terms of that oblique asymptote. So this is good practice on that front. But for now, I can see my non-permissible values. Oops, we forgot to do domain and range of that last one. I'll go back after. So non-permissible values, x cannot be positive 1, because that would make the denominator 0. Okay, this is going to be an asymptote because it doesn't cancel out. So already I can draw it at x equals 1. Again, putting in my scale a little bit here. And always remember to name your asymptotes. And then for my oblique asymptote, again, I'm going to do some synthetic division. So I'm going to go 1, going into negative 2, 5, and negative 2, 3. So my oblique asymptote is going to be at y equals negative 2x plus 3. So in terms of drawing that in, again, make sure your scale is labeled. Y-intercept at positive 3, and going diagonally downward, the next point would be here, here. So that's going to be my oblique asymptote. Again, on grid would be better. Y equals negative 2x plus 3. And from here, we just need to check some values. So again, we can make a table of values. It's kind of the quickest, simplest way, especially if this is on the calculator section of the exam. So we can test out like negative 2, negative 1, 0, and then 2, 3, and 4. Plug and chug, and we'll be able to fill that out. So we see that we're going to be positive and going to 2 here. So what's going to eventually happen is our graph is just going to follow along on the left side of that oblique asymptote. Let's switch to following along the vertical asymptote here. Okay, and then on the other side, we've got this vertical asymptote. It's happening here. And in terms of determining this exact intercept, because we do need to know our intercepts, this one's nice and easy. This one is 2 and 0. and our y-intercept is 0 and 2. This one here is also going to come from my factored version. So I look up here, and that positive 2 we see here came from this factor. So our other factor is going to be actually 1/2. So it's going to be at 1/2 end. Okay, so those are my intercepts. And then finally, I need to know my domain and range. And so domain, again, is horizontal, so that just that x equals 1 is the only restriction, so negative infinity to 1. Remember rounded brackets because we don't actually reach an asymptote. And then all the way up to positive infinity. Range, because we have that oblique asymptote instead of a horizontal asymptote, we don't have any sort of restrictions up or down. We could follow our graph forever in either direction without having to lift our finger. So we go from negative infinity to positive infinity. So that's kind of a good thing to notice about those oblique asymptotes. If for whatever reason my graph had ended up in these quadrants though, I would have had some sort of restriction on value to do with range. So just kind of as a heads up on that front. My domain and range for this function, since I forgot to do that earlier, if you didn't pause and do it yourself, would be for my domain, those 2 vertical asymptotes are my restriction. So I might do set notation for this one just because it might be a little bit easier. The x cannot be positive or negative 5. And my range, again, I'll do it in set notation just to be consistent, would technically be going just y cannot be negative 2. And so that's what we're going to see for those domain and ranges. So that's quite a few practice questions. If you want to pause now and give this one a shot on your own, I don't think that that's a bad idea. So we get non-permissible values when we factor things out. Our simplified equation is 1 over x minus 3. So it's just a general rational equation. So you should be pretty comfortable with the shape of that's going to come out to. Remembering that a higher degree in the denominator means that we are going to have a horizontal asymptote at y equals 0. And so then I'm not going to have an x-intercept as a result of that, but I will have an y-intercept at negative 1/3, and I get that by plugging in 0 into my equation here. So now it's just a matter of figuring out where all these things are. Because of my hole here, I could plug negative 3 in, and I see that it becomes 1 over negative 6. So it's going to be a pretty tiny little thing. So that's happening at x equals negative 3. That's going to be way close to the axis there. Our typical invariant points are 1 and 1 from my axis. So those are them. So that gives me kind of everything I need. And remembering that my negative 1/3 is my y-intercept. But again, being so small, it's not the most helpful. Again, we want to get super close to that asymptote when we're drawing these shapes. So that would be our graph. And so then it's just domain and range again. Domain being that restriction of our asymptote, which I forgot to label. So don't forget to name your asymptotes. X equals 3. And don't forget to make this a hole instead. That's going to erase that whole line. Ugh. This is where pencil is much better than stylus. Because at 3, there needs to be a hole. And keep going, just like that. So my domain, I need the hole and the asymptote accounted for. So if I'm using interval notation, it would go to negative 3, united with negative 3 to positive 3, just as if it had 2 asymptotes. And then from 3 to positive infinity forever to the right. My range then becomes a little bit different too, because I've got the restriction of negative infinity. That's great, but I actually hit my whole, which prevents me from having a value of negative 1/6. Negative 1/6 goes to 0, and 0 goes to positive infinity. And that's what we're going to see on this graph. So that's our domain and range here. And that is our last practice example. So there will be some homework to try. Make sure we're feeling comfortable with this idea. Key thing to remember is that, again, from the previous lesson, that whole idea of different kind of higher degrees being obliques versus equal degrees being just a shifted horizontal asymptote. That's going to be something that you want to remember from lesson 3 as we work in lesson 4.